kind of like orange. Can I close this? Yeah. You still see the background, right? I think so. Okay, so I think the next step is basically to go and check the how to translate the actual problem into a QO. I think that's what I want to do today. Because we've played with D-Wave, I guess we'll figure it out. We'll figure it out as we go. So Chicago Quantum Exchange, Chicago Quantum Summit, Chicago Quantum portfolio optimization D-Wave. Let's see what we get. So this is the paper. Let's take a look at the webpage. Maybe there's some links. So this is some news. And this is the Medium post, right? Let's get the PDF. And in the Medium post, maybe there's something there as well. So this is just okay, just a summary of this stuff. This is not interesting. So we construct stock portfolios based on our stock picking formulations from July 10th, 2020 data. After the US market close, we pick from a universe of 60 stocks, run them through our classical and quantum algorithms, and select 2 stock portfolios from the quantum portfolio results. Our starting point is 60 US liquid stocks. Okay, so but this is the so the mathematics and the computation, I guess this is the same paper that I'm going to open up right now. Yes, to find our specific portfolio size in a very few number of tries out of a large number of choices. So we see our quantum values override almost the entire efficient frontier, which shows us comparability between our CQNS formulation and the classic Sharpie Ratio. Okay, so we want to understand what the CQNS is, right? The CQNS finds high expected returns for certain level risks. Quantum is classical efficient frontier. Marker multiplier. CQNS. CQNS portfolio, CQR portfolio, GA portfolio, Universe 60 stocks. These are the results. Finally, we have no evidence that any of these portfolios are optimal or best or likely even on the top 25% of portfolios we could have selected. They were chosen based on prior 12 months performance, which is no guarantee of future results. What we do know is that we use a quantum computer for 20 seconds to look through 1.15 times 10 to the power of 18 portfolios, and we select portfolios that will track and measure against the universe of stocks they were selected from. So here we actually have the 60 stocks that they get. Now, and this is include Okay, they also have the indices and then data from Yahoo Finances of 4 p.m. CT on July 10, 2020. Okay, so with this we could reproduce at least a 60 stock one. We tracked 5 portfolios from market close to July 10 through market close August the 2nd. Let's see the results. Okay, but I'm looking for the CQNS. I have no business with any company stock like that. Okay, but there's no mention on the what is the particular CQNS, right? And I'm assuming that is then what should be explained in the paper. Let's focus on this today, okay? So we got the paper here. Let me open. Let me zoom it in. We investigate the use of quantum computers. This is the abstract, blah, blah, blah. Why is this scrolling so slowly? As usual, PDFs. Okay, so to find optimal risk versus return portfolio, an optimized portfolio based on the Markowitz formulation and the Sharpie ratio, a simplified Chicago quantum ratio, then a new Chicago quantum net score. Introduction. Okay, so here we have the Sharpie ratios, these things, right? So first, let's try to understand these. So what is the Sharpie ratio? Wikipedia. Sharpie Ratio was developed by Nobel laureate William F. Sharpie. I'm sure I'm pronouncing it wrong, and is used to help investors understand the return of an investment compared to its risk. The ratio is the average return earned in excess of the risk-free rate per unit of volatility, or total risk. Volatility is a measure of the price fluctuation of an asset or portfolio. Subtracting the risk-free rate from the mean return allows an investor to better isolate the profits associated with risk-taking activities. The risk-free rate of return is the return of an investment with zero risk, meaning it's the return investors could expect for taking no risk. The yield for a U.S. Treasury bond, for example, could be used as a risk-free rate. Okay, so you're okay. So what this is essentially doing is kind of removing what you would consider a safe investment from whatever you want to take, and then you can have a better understanding of the risk associated with taking that, right? Because you could just as well put the money somewhere else, like on a U.S. Treasury bond, and then generally the greater the value of the Sharpie ratio, the more attractive the risk-adjusted return. The greater the value, the more attractive the risk-adjusted return. Return of the portfolio minus the risk-free rate divided by the standard deviation of the portfolio's excess return. Subtract the risk-free rate from the return of the portfolio. The risk-free rate could be a U.S. Treasury rate or a yield. Divide the result by the standard deviation of the portfolio's excess return. The standard deviation helps to show how much the portfolio's return deviates from the expected return. The standard deviation also sheds light on the portfolio's volatility. Okay. Okay. But I guess, so here's an example. But I guess the so let me understand that. So you have the return of the portfolio, and you're removing the risk-free rate. So okay, so if we ignore the standard deviation for a second, that alone would be that the bigger the number, the bigger the numerator here, the better, because it means that taking the risk is really worth it. Because if you could, if the number is small, it means you could as well just put the money into something that's safer. That's it, right? Like something that's risk free. And then the standard deviation. That is cringy, but like, let me recap that. So the standard deviation is a statistic that measures the dispersion of a data set relative to its mean. Okay, and it's calculated as the square root. Okay, so this basically is how calm it is. Like, so it calculates how much, like it tells you how much it varies from its mean values. And so if it's really high, it means that like it probably, there's like, I mean, it's what they say here is like there's a lot of volatility, right? So the smaller the better. The smaller the better. Yeah. So you're correcting, you're adding this correction of, you're saying if it's quite stable, then your number stays big because your numerator is big. And then you divide it by a small number, it's still a big number. Whereas if your standard deviation is big, then you're going to get like a small number, which is what you want, because it means that like there's a lot of volatility, and so that is maybe not attractive, right? Or it's an indicator for risk as well. Okay, makes sense. Now, why this can't be implemented into a quantum, into a D wave, into a cubo? I guess it's because of the why can't this be implemented into a cubo? So what do we have here right away? This will instruction as follows. Then we begin our exploration with a Sharpie Ratio. Okay, so I see here the standard deviation, and then I see the RA minus RB plus RB, where beta is the ratio of covariance of a portfolio with a market over the variance of the entire market. RA is the return of the collection of assets. RB is the risk-free return. And the is it lambda? No, it's not lambda. It's theta, whatever. Is a standard deviation of the collection of assets. W is the vector of weights for assets in our portfolio. We can also see the Sharpie ratio in matrix form. What is E though? What is this E in here? So you're taking, W is the vector of weights of for assets in our portfolio. Okay, so this is like, okay, so what you're doing is you're trying to calculate the Sharpie ratio of a portfolio. Of a particular choice, right? And W tells you these, right? Like it's the weights, as in like take, invest everything in two of them, or invest everything in like, I don't know, like, do 50-50 or in two of them, so, or do like 30-70 or something like this. Beta is the ratio of covariance of a portfolio with a market over the variance of the entire market. I don't know why, but Simulation of the collection of assets, and W is a vector of weights for assets in our portfolio. We can also see the Sharpie Ratio in matrix form. Why is this a matrix form? From who developed the Chicago quantum ratio, which is W times the covariance, where cov IM is the covariance of the ith asset against the entire market. This is a slight improvement over the Sharpie ratio in terms of computation, as we need not consider nominal assets. Risk-free investments have a near-zero covariance with the entire market. Covariance is like how they like differ from each other, right? I keep mixing these concepts up. Joint variability, exactly. The joint variability of two random variables. If the greater values of one variable mainly correspond with the greater values of the other variable, then the same holds for the lesser values. The covariance is positive. Okay. So it's negative. It's like these. It's positive. It's like these. If it's zero, it's like there's no. So what they're saying is that risk-free portfolios have a low covariance, right, with the market, because this means they're totally not related to the market because they are risk-free, and so they, okay, yeah, you could say so. Near zero covariance. Do they though? Like a risk-free investment, it means it's an investment that it's so where you're always winning, right? And so, yeah, okay, the entire market, like, but I wouldn't say it's zero, right? Like, I really wouldn't say it's zero. I mean, it depends on the market. It depends on it really depends on, yeah, but okay. We can also reformulate CQR in matrix form. It's not with matrix form, so but I'm missing something here. It's like, shouldn't there be like a sum, or the equation is weird because it says covariance IM is a covariance of the ith asset against the entire market. Okay, so it's a CQR for one asset. Is it like the sub A here means it's one asset, right? No, it's of a collection of assets. It's the actual peak that you do, okay. But then there's something missing here. Because this is a term that's like the ith asset against the entire market. Let's think about this for a second. So CQR is a ratio that tells you, so W is the vector of weights for assets in our portfolio. And I assume the weights mean like, what are we picking, right? So if the weight is 0, it means we're not picking this one. If the weight is, and I guess the sum of weights must be 1. It's not, okay. It doesn't have to be 1. It has to be below or equal to 1. Could be bigger as well. You can decide to invest more. I don't know what the weights are. So, but this is weights times the covariance. And so what you want to do here is but isn't that implying that you're never going to peak? Because the risk-free investments will have a covariance that's like close to 0, a covariance with the market, according to their own statement, right? And so then you're going to have like the CQR is going to be 0. Because this ratio seems to say you're basically looking for positive covariance, or like the higher, I mean, that's directly proportional to the covariance, right? It's just corrected by the standard deviation. So, and and the original Sharpie ratio is basically if, no, I think it's correct. So if an asset is kind of almost risk-free, the Sharpie ratio will actually be really small. Exactly. And here with the Chicago quantum ratio is the same. Because if it's almost risk-free, then you're going to have covariance close to 0, and so the CQR will be actually close to 0. Okay. I think it makes sense. It's still, I think, it's a big statement to say, though, that covariance with the market is close to 0. I mean, I don't know. I'm not intuitively thinking. I mean, if the market is doing well, right, then you should have positive covariance, shouldn't you? Not 0 covariance. Because with a risk-free investment, you're always winning. Okay. Risk-free investments. Let's see if I can Google that actually. Like, zero beta portfolio. Covariance definition. Covariance with the market. covariance measures how stocks move together. Positive covariance means stocks tend to move together when their prices go up or down. A negative covariance means the stocks move opposite of each other. Covariance is used to measure the correlation in price moves of two different stocks. Isn't it wrong to compare then sort of like an asset and the whole market? Like, isn't that actually essentially wrong to compare that? Like, aren't you comparing apples and pears, so to say, or apples and oranges? I think it's a sentence. Okay, but we'll yeah, we can also reformulate CQR in matrix form. We explore these formulations by a variety of classical methods, which one will find in 3. Both formulations are ratios, and thus neither is properly suitable for a quantum annealing solution, as the wave requires a linear quadratic form. We attempt to rectify this by exploring the natural logarithm. What is E? What is these? The capital E. Have I tried to? Okay. This, however, causes a different set of mathematical problems in formulating a consistent quadratic form. Finally, we settle on the Chicago quantum net score, which is given by these. Wow. Okay, that was a big step. So first they attempt to rectify this by exploring the natural logarithm. Attempting to rectify this, however, causes a set of different mathematical problems in formulating a consistent quadratic form. Why? I don't know. So what CQNS is basically for W and alpha. Okay, so RW is a weighted portfolio, and alpha is a real number. In most experiments, we choose an equal weighting, where n is the number of assets included, and we choose alpha near 1. These are not requirements, but they do make the computations in the wave slightly easier. There is a wide open question as to finding optimal weighting and optimal alphas. We explain how to formulate a quadratic form for use in D-Wave in, I guess this is Appendix 4. Finally, in Appendix 5 and 6, we give our results visually and mathematically and discuss our future work. What is this? Is this what, like energy? Like, I don't know, what is this? So the variance of the portfolio minus minus E. What is this in the portfolio? To the power of 2 plus alpha. Okay. So where are these appendices? If this would scroll smoother. Oh no, this is not appendix, it's like chapter 4, I guess. The main thrust of this research is in fact how to formulate a QO which, when presented to you, produces similar results to the classical Sharpie ratio. Consider the following. The Sharpie ratio is defined above in 1. The numerator can be expressed as a simple dot product where mu and w are the expected return and the relative weight of the ith acid respectively. The expected return and relative weight. Okay. But that's not true, right? Because it's not the expected return. Like you gotta remove the risk-free investment thing. The denominator can be expressed as a square root of a quadratic form, where Q sub I is binary classifying whether the ith asset is in the portfolio or not. V sub I is the variance, and cov ij is a covariance term between asset I and asset j. So I guess that is the formula for standard deviation, right? Like standard deviation. Formula. Math is fun. Math is fun. Why? Sorry, it's a bit late. But it's fun. Yeah, that's the square root. Okay. And so essentially that's the square root, and then the covariance. Also recognize that Sharpiration is not a proper quadratic form and does not solve the wave system. When the Chicago quantum S-core solves this problem, can be presented as a quadratic form. Okay, but they don't explain. Or do they explain how to develop the QO here? Consider the universe U of n acids. When dealing with a single acid portfolio, we only consider the linear terms in a QO. In particular, when we have a lower triangular matrix or a zero diagonal matrix, products of the form. But as we pick off only the linear terms in this case, we concisely model the inverse Sharpie ratio on qubits and use a penalty on the couplers. Moving to two or more acids, we have substantially more work to do. Looking at a single acid, there are two covariance terms to deal with, and we can embed the inverse Sharpie ratio directly into onto the qubits. We create a unique QO for each size portfolio evaluated by applying the weights directly to the matrix. So Qi and Qj can remain binary. We divide the linear terms by n and apply the linear affine transformation. We divide the variance terms, diagonal entries, to avoid duplication, and divide the covariance terms of diagonal entries by n squared to avoid duplication. We then apply the quadratic affine transformation. Then we assemble the matrix and reverse the sign on the linear terms. Finally, we apply a scale factor and write it into our n by n matrix for processing by D wave. Why a matrix? First of all, Cubo matrix. Oh, here we go. So what is this? Why a matrix? I'm need to stop it since there are several types of cube matrices. I won't know what should be used D-wave, mainly in D-wave hybrid. Type 2 D-wave cube matrix A is upper triangular, linear coefficients main diagonal terms, quadratic coefficients upper off diagonal terms. With upper triangle with the other linear coefficients. I believe that this quadratic dictionary must be the type 3, upper triangular with all diagonal entries equal to 0. Yeah, so my questions are, what are the correct and best types of cube matrix to work in the wave applications? Hello, John. The answer to your question depends on your workflow. It is possible to solve cubes directly with many D-wave tools. For example, D-wave sampler through the sample cubo function. In this case, the proper format is upper triangular with linear terms included in the diagonal. Okay, so these are the linear terms. Say you have, it's been a while without using the pen. I'm gonna go for some coffee or something. Does this work? Does this work? This works, but I think I can't paint in here. No, why I can't paint? Why I can't paint? Because I can only paint on a tab. That is not this one. Whatever. Because I'm recording on another browser. So, okay, but so basically, if we have, say, Q, like sort of Q1, Q0, Q1, Q2, so those are the linear terms, and then this is so Q0, right? So this is 0, 0, 0, 0, and then this is like 0, 1, yeah, 0, 2, and then 1, 2, yeah. The rest are, that's why it's just upper triangular, because the other values will be the same. So there's also a more general way to solve, to write both cubes and Ising problems referred to as the binary quadratic model. This form separates the linear and quadratic terms. In this case, you can use a common sample function. That's what we used in bracket, actually, right? I think that's what we used in bracket. Okay, so this is what I mean by the matrix. So each matrix, it's each element of the diagonal, it's one of the assets, right? And so basically one asset is just like, if you just want to pick one asset, you using use penalty for couples. One's prefers with the highest ratios. Consider universe U of n assets. When dealing with single asset portfolio, we only consider the linear terms in a cubo. In particular, when we have a lower triangular matrix or a zero diagonal matrix. I'm not so sure that is entirely fair to do. What are we? So actually, why are we checking the covariance between two assets that we pick? I don't know, I might be overthinking this. It just goes really fast. Like, then we're going to express a simple dot product where the ith asset is the not is the variance and the covariance. The covariance is the covariance between assets I and j, which in the case of like one asset, that term doesn't exist. And so we only care about the variance. That's what this is saying. So you only care about the variance. And so as you're then solving a cubo that's like that, the cubo solution is basically you're trying to find for something that minimizes the energy, right? So it minimizes the actual result of the cubo, and so you're gonna go with the asset that has the lowest variance. Are you? Yeah, the lowest variance. This means highest ratios, right? Because this part here is not going to be in there. But what is CQNS finally? I hate that this scrolls so slowly. So this is CQNS. So this is variance minus whatever the crap this is. What is this E? How can I find these? How are these things called? Is it like math? Probably. No, that's not the capital E that I mean. Math wiki. Cookies. Accept the cookies. Expected value? Is it expected value? In applied mathematics? Oh, come on, commercials. Let's just... That's what makes the most sense given the context of these being statistics. It's the expectation value of... But I don't know where they take these from. Can this please scroll? Okay, from here. The expectation value. So this is from here. The expectation value being the average. Okay, so that would be then the average. Yeah. Okay, I think I understand what these mean. So it's the average kind of return, like risk-related return, right? And so CQNS. So what they do here is they take the variance of your portfolio and minus. No, that wouldn't make sense. Minus the expectation value, or minus the whole returns, like the returns, and it's even exponential. I don't understand how they get here. Like, how do they get to this equation? I don't know. I don't know what the E means. Probably expectation value, but the expectation value of the weighted portfolio. Still, we find that the Chicago solves this problem and can be represented as a quadratic form. How? So consider a universe, blah, blah, blah. So what are these things? EQE. Mm. Mm. So we embed the CQNS on the D wave by writing the expected returns onto the linear terms. Okay, so what you're doing finally, so what you're doing is you're embedding this by putting the expected returns onto the linear terms, and then both variance and covariance onto the quadratic terms. From here, the D-Wave inspector shows how the system encodes and embeds assets into physical qubits. An attempt at changing the formulation by manually embedding terms to respect the reordering of assets does not yield substantial improvements. As we increase our asset size, we see that for a fully connected qubit, D-Wave requires multiple qubits in chains to leverage the available connections in order to group in other groups of chimera structure. Increasing our portfolio size above 40 would result in increasing qubit counts utilized to support multiple chains, and the potential for increased chain breaks. We see consistent results with 40 assets when we tune the chain strength and scale factors. So, if I understand this well, it's basically you put the variance in the terms, and the expected returns into the terms, and then both variance and variance and covariance of diagonal into the quadratic terms. So what you're essentially saying is They're essentially saying you want to minimize, returns, expected returns as in like, the higher the better, but you're trying to minimize that, right? So, yeah, it's not really clear how this is done. Like, this is super harsh to actually reproduce, I think. When exploring portfolios of different sizes, we present a different matrix to the way for each desired size portfolio. We add a penalty for exploring portfolios of different sizes while maintaining accurate values for the desired portfolio size. The intuition for this follows closely from converting a cube into an Ising model. In order to convert a cube into an Ising model, we consider transformation on the binary vector x. This transforms x into where c is a vector of matching length and k is a constant which we can remove from consideration. Since we're only looking for the location of the lowest energy level in the z coordinates. Blah 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 blah. Definition 1, visualization. Results. Download 1 year of daily market data for a specific set of n assets and indices. Current as of that moment, hold the data for all experiments, calculate covariance of each asset with the market and beta. And then 3 based on log results. Covariance terms between assets. Underlying and summary values including Sharpie Ratio and Chicago Quantum score for an all-asset portfolio. Derive a cube for each portfolio size. Visualize minimum CQN values on multiple cube matrices. Shift each cube to increase likelihood of choosing a portfolio with a fixed number of assets. D-Wave using appropriate range of portfolio sizes. D-Wave is also see the generic algorithm and compare values. The following figures 34, gives some idea how well the quantum computer performs. Yeah, it almost feels like I haven't moved much forward. What time is it? Because I basically wanted to try and understand the Kubo, but like I'm like not entirely sure I understand. So it's definitely CQNS. But I don't know what this E means, and I don't know how can this be represented in the Kubo form, right? So simple dot product. Okay, so what they're saying here is they're saying that yeah, you can basically so you can basically the numerator is basically the expected return kind of multiplied by you're multiplying it by each asset. Okay, yeah. Mu being mu I and wi being the expected return relative weight of the ith asset. The denominator can express the square root of this quadratic form. Oh, now I know where the 2 comes from. Okay, because this is it's 1 divided by these, and so okay, so it's 1 divided by these. And no, can you do that? I guess that's where these comes from, right? Like they just go and say that's where the 2 comes from in the in the formula below. Where is it? I'm so slow. I'm so slow. Where is it? Where are you? Yeah, I don't know why these things don't scroll properly. No, that's not what I want. Ah, there. That's where the 2 comes from, is it? Is it? I think so. Because we're not. Because you want to have the inverse of. Well, what is this E? Mm. Mm-hmm. Mm-hmm. So this is the denominator, and then it's basically the. This is not portfolio. It's the variance, and so you're taking the variance, and then you're also taking the covariance of the elements. Qi, Qj. So this is what we. This 1 divided by like u square root of u is just like representing like this being normalized, I guess. I guess so. But I'm not so sure I understand the shifts and stuff. That's way more complicated than I. Okay, so what I'll try to do next time, I need to get some sleep, I think. How would the cube look like for a 2-asset? How would the cube look like for like a 2-asset portfolio? Let's say we're going to pick 2 assets, okay, out of 40. Let's try these, and then maybe we'll download the data next time, and so we can start playing with this. Because It's shift factor. This shift factor is what the heck? What is these? When exploring portfolios of different sizes, we represent a different matrix to derive for each desired size of portfolio. We add a penalty for exploring portfolios of different sizes, while maintaining accurate values for the desired portfolio size. So you're adding something to it, so those values kind of are not definitely close to the lower values of energy that you're looking for. I understand that, but it feels okay because you want to avoid that it peaks more. But like, if you just want to peak 2, then why do you even need these? Why cannot you just have like the 2 terms? Okay, no, because you need to have all like Q's, like the Q from Q0 to Q like 39, because you need to pick 2 out of all those. But you want to have a constraint that tells you just pick 2, and so you have to limit. So you have to add shifts. Okay, I get it. So you have to add shifts. I think I start to get a picture of these. So you have to add something that makes those solutions more expensive. Okay. What I don't fully get is the I don't fully get the oh, I hate scrolling. I should just use a PDF reader, man. It's just yeah. Cool. Whatever. I can't find the. Can I just find this file? Next time. I think I have to go, sadly. Yeah, it's been a long video. But I think I started to get an idea of the shape of the cubo. So you're basically having the expected returns are the coefficients of the linear terms, and then the quadratic terms, or the terms, I guess those are the quadratic terms where like you consider 2 of those. See, I'm not entirely sure I get the whole cubo thing yet, but I yeah. So those are the quadratic terms, I guess. Right? So in this case, the terms is the sum of the variance and the the variance of asset 0. Wait a second. Why would it be the variance of asset 0? I guess it's the variance of each asset. The variance of each asset plus, I guess that's what you want, the variance of each asset plus the covariance. This will mean that you're penalizing by assets that like behave differently, and I don't know if that's a good. Because you have a high covariance, it means that they behave really similarly. And so if you have a minus, it means they behave opposite. And I don't. So it was a standard deviation, and it was the volatility, right? Of your all. Yeah, okay, of your all portfolio. So you want a portfolio that's not really volatile. But this means that it always kind of. Okay, so you want assets that between them they have like a low covariance, right? Right. Because if you have high covariance, then you're gonna have like a lot of volatility in there. I guess so. I guess so. But okay, I guess next step will be get the data, try to play with it, just go hard on these, because otherwise I can just spend hours trying to understand that, but like not make any progress. So the embedding part, and then we'll take a look at the transformations later on. Okay, I mean, it doesn't seem BS to me, right? It's just a really at the end of the day, it's like a model, right? So you have a model, you're building a model, and then you're basically, I guess, the what you're doing is it's like the quantum computer is allowing you somewhat to take into consideration, right, like all the 40 different assets and their combinations, which is a number that it's intractable with a classical computer. It's intractable to brute force, but still. Once you have the qubit, you're looking for the values that like minimize the energy, and you're hoping to achieve these by annealing. So basically, by naturally evolving that, and so because your it's so you're relying on nature to give you that minimal value. Okay, I guess I think I should leave it here. It's been a long video, and I don't feel I've moved forward a lot, but maybe.